In the last lecture, we looked at the mass transfer around a single dense particle. However, a packed bed reactor has many particles. So how can we use what we discussed in the last lecture to better understand the behavior of these catalyst particles as you move along the length of a packed bed reactor? So to do this, let's consider the same reaction that we did in the last lecture, right? Just A goes to B. It's the simplest reaction that we've considered. And we know for this in a packed bed reactor, we normally would be inclined to write DFA dW is equal to RA prime. Now, this is fine, but this doesn't help us necessarily to immediately answer some of the questions that we might have given to the last lecture. So let's do two things here. The first thing is let's learn how to express RA in terms of the catalyst surface area, because remember, that's where the reaction is actually happening on the, at least in this example, right, the exterior of these dense particles. And then second, let's get things in terms of the tunable parameters from the last lecture. Remember, we had velocity and the diameter of the particle. So if we're going to use what we did last time and understand how at least those variables start to influence how packed bed reactors behave, we can't do it just simply based on the catalyst weight, because we know now that there are multiple ways that we could implement the same weight into a reactor. And then this will give us some generalizable thing that we can talk about moving forward. And it'll allow us also to easily or more easily transition when we start to discuss internal diffusion as well. So to do this, let's define the areal rate. And that is RA double prime. Okay, so we're going to call this thing the areal rate. And we can do this very simply by defining this areal rate as equal to RA prime, right, which is the rate based on the mass of the catalyst, divided by the surface area or the specific surface area. And we're going to call that S sub A. And this thing has units that is essentially just meters squared per gram of catalyst, or at least it's some length squared over a gram of catalyst. So for some materials, especially nanomaterials, meter squared per gram is a very, very good metric. Sometimes if you have large, like 100 micron size particles, you'll discuss it in centimeters squared per gram, but still it's some length squared, right, to get us an area per gram. And what this means then, if we've defined RA double prime, this areal reaction rate, as equal to RA prime over the specific surface area, that just means that we should be able to substitute RA prime in our equation to the left as simply the areal rate times the surface area. And I'm going to go ahead and do that. So now we have DFA dW is equal to RA double prime times the specific surface area. Now, we also know from our derivation when we were trying to get to this equation to begin with, that DFA, here maybe to keep this organized, right? So we know that DFA dW is equal to DFA dV times 1 over this thing that we called rho B, or of course rho B was just the mass of the catalyst divided by the volume of our reactor. And believe it or not, for us to get things in terms of the variables that we discussed last time in an easy to implement way, we're actually going to revert back to this and use the fact that dF dV is equal to rho B times DFA dW. And actually the better substitution here then is just to end up with this equation where DFA dV is then equal to rho B times SA times RA double prime, right? And basically we've just introduced rho B back into here to get things in terms of volume, okay? And we're gonna do this because in a minute we're gonna go to length, but I don't wanna do that quite yet. So if this makes sense to everybody, I would now like to have a look at this term here. this rho B times SA and try to tackle what that really is. And we'll do that by looking at the units. So if we look at the units for rho B, right, we already said that this is basically the catalyst mass divided by the reactor volume or the bed volume, right? And right, the catalyst bed volume times SA, which we said was surface area per catalyst mass. And if we do this, right, we can get rid of the catalyst masses and we get something that's like surface area over the bed volume or the reactor volume. Okay, and that has an interesting unit of meters squared per meter cubed. And one of the things that we like to do is actually define this product as a variable AC. And why in the world would we actually do that? Because it's easily definable for any geometry. So for a cylindrical vessel like a packed bed reactor, we actually can find that AC is equal to 6 times 1 minus theta over dP. And theta here is the porosity. And of course, the diameter of the particle, or dP is the diameter of the particle. And we can do that for any shape. Now, at the end of this video, I will specifically derive this. And so that'll be like bonus material. You guys can come back later and look at that. It'll be marked in the description on YouTube, and you'll be able to go ahead and just click at the end of the video and watch a small derivation on this. But I won't do that right now because I don't want us to get sidetracked here. I just want you to know that AC is definable based on particle shape, particle size, the geometry of the reactor, but it's a constant essentially once you know the parameters of our system. And because of that, we also can say then dFA dV just equals this thing AC times RA double prime. Okay, and this is the thing here, at least for step one of what we're trying to do, where we're trying to get, right? This is getting things in terms of this areal reaction rate, and we still have properties of the packed bed reactor in our equation. Okay, so what to do now? How are we going to actually use this to solve problems? Well, we said that we would like to introduce other variables that we discussed last time. So in AC is the diameter of the particle. But what about the velocity? So how are we going to start to get the velocity here into this expression? And we're going to do that by making two substitutions. The first thing that we're going to do is note that the volume of our reactor is actually simply the cross-sectional area times the length, right? And we'll use AC for cross-sectional area. We're going to have a bunch of different areas that are floating around. So let's try to come up with one symbol for each of them. So this one is the cross-sectional area, okay? The other thing that we know, of course, is that the flow rate of A is equal to the concentration of A times the volumetric flow rate. But the volumetric flow rate is just equal to the cross-sectional area times the linear velocity. And we're actually going to use that, this as an opportunity to introduce velocity into our system. And so our derivative here on the left-hand side of this equation becomes d times CA times the cross-sectional area times the velocity, dV, or the cross-sectional area times the length, right? And that's equal to AC times RA double prime. And if we have a cylinder, like most reactors are, well, cylinders have a constant cross-sectional area. So that's not going to change over the length of the reactor. So we actually can cancel those two out. And we end up getting an expression that now has the differential of CA times the velocity, DL, is equal to AC times RA double prime. Now, in an equation like this, where A goes to B, we have the same number of moles on both sides of the equation. So delta N is 0. That means that the volumetric flow rates are the same in the gas phase. Or if we have a liquid phase reaction, you also would have constant volumetric flow rates. So from here, we're going to say, look, in this example, we can assume, because of either one of those things I just said, that the volumetric flow rate is equal to a constant. And why is that important here? Well, if the volumetric flow rate's constant, that means, and of course the cross-sectional area is constant, that also then means that the linear velocity is equal to a constant as well. And that allows us to pull it out of the differential. And we end up getting just the velocity times dCA dL is equal to AC times RA double prime, okay? And now what we can do is look at how the velocity is going to change the concentration profile along the length of the reactor. Now, how are we going to do that? Well, in the last lecture, we actually derived a really nice expression for RA, right? We said that minus RA double prime was equal to what we called KR times KC times CA over KR plus KC. And for those of you who didn't remember that, remember KR was our reaction rate constant, right? When we were kinetically limited. KC is the mass transfer coefficient. And in the last lecture, we started to talk about how we could calculate this external mass transfer coefficient. And if you remember in that lecture, we had two cases. One where we were kinetically controlled. And what that meant was that the reaction rate constant, KR, was much greater than KC. And we also had the case where we were mass transport controlled. And of course, the velocity, as we talked about at the end of that lecture, doesn't have any effect on the kinetics when you're mass transport controlled, other than changing the volumetric flow rate and the residence time. But it doesn't change how anything interacts with a catalyst particle. But if we are mass transport controlled, this simplifies to something very simple. And in a case where then KR is much greater than KC, well, then this actually simplifies to minus RA double prime is equal to KC times CA. And of course, we're trying to talk about how mass transport is going to affect our reaction. So this is the case that is at least the most interesting to us. So let's then combine these things together, and we'll find that the linear velocity times dCA dL is then equal to minus AC times KC times CA. And of course, we can solve this, right, with some initial conditions. So we know that at time or length equal to 0, right, at the beginning of the reactor, that CA is equal to CA0. All right, so let's try to solve this. And we're going to do that by bringing CA to the left side. We're going to bring everything else to the right-hand side of this equation. So we get dCA over CA equals minus AC KC over the linear velocity times DL. And we can integrate this, right, from CA0 to CA and integrate this from 0 to whatever length we are interested in. And of course, the left-hand side here just becomes the natural log of CA evaluated from CA0 to CA. And then the right-hand side just becomes equal to minus AC times KC over U times the length. And the left-hand side, of course, is just the natural log of CA over CA0 equals minus AC KC over the linear velocity times the length. And then we could solve for CA, right? So CA then just equals CA0 times the exponent of minus now KC times AC over the velocity times the length. okay? And note that this looks very, very similar to something that we've derived in the past. Remember, it seems like forever ago probably, but we had derived that, Ca was Ca0 times the exponent of minus K1 times tau for a plug flow reactor. And we could also get a very similar looking expression if you assume that you had a packed bed reactor as well. But here, I mean, this is, this kind of correlates with this. And of course, the length along the reactor at some flow rate is also related to the residence time. And we've had a little bit of practice during this semester in converting between those two. Now, obviously, these aren't the same, but it is nice, I think, for us to see that, even when we start to take alternative pathways and we start to look at even more complex phenomena, the math and the other things that we've done earlier in the semester don't vanish, right? We still get solutions, we still get functional forms that look familiar, at least at times when we have been able to strip things down. Now, we could ask ourselves, what if we wanted this in terms of conversion, right? We've used conversion many, many times throughout the semester. And in fact, for gas phase reactions where delta N is not equal to 0, almost all of our solutions have been in terms of conversion because it makes it easier for us to express Ca as a function of Ca0, epsilon, and conversion than it is for us to do other things, especially too when you change the temperature or pressure in the reactor. So for us to do that, right, let's go back to right before we were going to integrate this thing, right? So let's look at maybe this form of our equation. Well, we know then, if we're going to do that, that U times dCA dL equals minus AC times Kc times Ca, okay? And if we're going to do this, well, how do we introduce conversion usually? Well, we start with the flow rates, right? So Fa is equal to Fa naught times 1 minus x. And then, of course, this is just Ca times the volumetric flow rate is Ca0 times V0 times 1 minus the conversion. And it's the velocities or the volumetric flow rates that actually bring us epsilon and all these other things. But remember, in this problem, we said that because delta N was 0 or it's liquid, choose your own adventure there, that we know that the volumetric flow rates are equal. So that means that Ca in this problem is just Ca0 times 1 minus x. And if that's the case, then the left-hand side of this equation just becomes the velocity times d of Ca0 times 1 minus x dl is equal to minus AC times Kc times Ca0 times 1 minus x. And of course, this dCa0 times 1 minus x is just minus Ca0 times dx. And we've done that a couple of times as well. And so that makes the left-hand side of this just minus U times Ca0 times dx dl. And that equals minus Kc times AC times Ca0 times 1 minus x. So the first thing I'm going to do here is divide everything by minus Ca0 because the Ca0s are constants. They should cancel here, and the negative sign should cancel as well. So we're going to get this linear velocity times dx dl equals Kc times AC times 1 minus x. So let's rearrange this just like we ordinarily would. And this just becomes dx over 1 minus x equals Kc times AC over the linear velocity times dl, okay? And we're going to integrate that, of course, from 0 to conversion and 0 to the length. And so our solution here, right, is just the natural log of 1 over 1 minus x equals Kc times AC over our linear velocity times the length, okay? And this gives us an expression where we can either calculate the length of the reactor required to achieve a certain conversion, or conversely, if we know the length, we could calculate the conversion given the reactor length, and then these other properties, right? Knowing the mass transfer coefficient, knowing the linear velocity, and knowing that geometric factor, AC, okay? All right, so the last thing that I want to point out here, and then I will stop for a moment and just like let everybody have a chance to ask a question. Remember, more generally, right, minus RA double prime, or actually, I actually like writing RA double prime, is just equal to minus KR times KC times CA over KR plus KC, right? And we derived this in the last lecture, and we even discussed it just a moment ago, right here. And then we said, well, look, if we're mass transport limited, you know, then derivation follows, right? And all these things that we just did when we're only mass transport limited. But just like I said in the last lecture, things are not always that simple, where you're either kinetically controlled or mass transport controlled. That sometimes the rate constants, KR and KC, will be similar in size. And then you're going to have mixed control, where both kinetics and mass transport simultaneously influence what you're doing. And of course, both of these derivations we just did, you could sort of redo with this full functional form. Now, I'm not going to do that for both of them because the math is very simple and straightforward, but I do want to do one just so you guys can see this. And remember, we got to this point where the linear velocity times dCA dL was just equal to AC times RA double prime, right? So when that's the case, well, we have our rate here, right? So it's minus KR times KC over KR plus KC times the concentration of A. And again, right, use a constant in this particular case. And we could do the same stuff that we just did a moment ago and rearrange this equation. And if we do that, then dCA over CA equals minus AC over U times KR KC over KR plus KC times DL. And we'll do the exact same integral we just did a second ago from CA0 to CA, and this is from 0 to L. And if you look at the solution here, right, where CA is equal to CA0 times the exponent of minus AC over the linear velocity times KR KC over KR plus KC times the length, right? This is identical to what we had just a moment ago up here, except now we have all of the coefficients here. We don't just have KC, okay? So, right, that functional form looks very, very similar to what we've done before. And the only thing that's different is that this bit here is slightly more complicated, okay? So until now, what we've done so far this morning in, about 25 minutes is we've talked through a couple of things. The first one was the definition of the areal reaction rate, that we realized that if we're going to have a bunch of catalyst particles in a bed, that they can have a lot of physical properties that get you to the same mass loading, which is the thing that we talked about previously. So we transitioned a little bit to a form that gets us closer to understanding the properties of the particles and then how it would influence the rate. Okay, and the areal rate helps us to do that. Okay, then the second thing that we did was to understand, or hopefully link, how the variables that were discussed in the last lecture, like the linear velocity and the diameter of the particles, would influence our reactor level variables, right, as we're moving along the length of the PFR. And so we ended for mass transport control with this function, and then we also have one versus conversion. And it's interesting to note here that if you look at these, well, how are our physical properties here? Well, if you look, for example, here's the velocity. And if we were to increase the velocity, what would actually happen? Well, if we increase the velocity, it has two different effects, and one of them is kind of invisible here. Because remember, both the diameter of the particle and the velocity are also contained in Kc. So simply increasing the velocity, you can't just look here, right? You also have to look here. Also increasing or changing the diameter of the particle. Yes, the diameter of the particle is in AC, as we talked about, but as we said in the last lecture, it's also in Kc. So we're going to talk about that a little bit, and I'll give something that I think is an interesting example of how those variables play against one another in just a second. But before I do that, I want to open this up to you guys to give you the opportunity to ask any questions you might have about what we've done so far this morning and how we've extended what was done in the last lecture.
I was going to ask for like a non-constant volumetric flow rate. Would that be hard to implement, or would you just use like the epsilon x terms that we've derived?
So that's a really good question. So there's two changes that you would make here for a non-constant volumetric flow rate. The first one is in the epsilons, just like you talked about, right? That's a very good catch here, right? That when this isn't true, then we end up with things like Ca is equal to Ca0 times 1 minus x over 1 plus epsilon x times, right, T0 over T times P over P0, right? So that would be implemented. That would be implemented here. The other thing that we would have to do, though, in that implementation is also think about how that affects the linear velocity here, right? So we would implement those changes simultaneously. And you would end up with basically having the functional form for the volumetric flow rate in here also, before you would convert it into the cross-sectional area, because you still need to consider, because you know how it changes with a constant cross-sectional area, right? We know the form, right? V equals V0, I just wrote it, right? But 1 plus epsilon x times T over T0 times P0 over P, or you guys know, I will often, I think this is right, but sometimes I flip these by mistake. So if you were to do that, right, then this would be like the linear velocity times AC is equal to the initial linear velocity times AC times 1 plus epsilon x times that stuff, right?
Right.
And so this is how you would end up implementing it here. So you would put that in there, right? Or actually it would be, right, these would go away, the ACs still go away. And so then this thing would become equal to here. I mean, we can just do it, right? So let's do CA times U, right? So that thing just equals CA0 times 1 minus x over 1 plus epsilon x times T0 over T times P over P0, right? That would be CA. And then we would multiply this by U, which is U0 times 1 plus epsilon x times T over T0 times P0 over P, right? And if we look at this, a bunch of stuff is going to cancel, right? So those will cancel, those will cancel, and those will cancel. And you end up getting that that's equal to CA0 V0 times 1 plus epsilon x. Oh, sorry, 1 minus x. Ah, that was almost beautiful. And then I messed it up. There we go. Okay.
Okay, is that supposed to be U0 in red?
Yes. See, I made 2
Okay,
mistakes.
thank you.
U0, not V0.
Okay.
Yeah.
Thank you.
Yeah, no, but that's a really good question. I mean, you're certainly going to see a case during the course of this semester where the volumetric flow rate is not constant. So that's a very good question. All right, great. Anybody else have a question that they want to ask? All right. If not, let's keep going. And I think that I have an example where these variables all play against each other, and it makes you think a little bit about what is influencing what. So if you remember, for a kinetically controlled reactor, we've solved a couple of problems where instead of having just one huge reactor, we split it up into multiple plug flow reactors or multiple packed bed reactors, right? So we took some condition where we had, let's say, an initial reactor where we had, V0 and we had some volume 1 and we had, some conversion along the length of the reactor. And what we did was say, you know what, you can run a bunch of parallel tubes instead. And so what would happen then is that you would split this to 3, let's say 3 reactors. I'm just going to use 3 arbitrarily. Okay. So you would have 3 reactors that were 1/3 the length or 1/3 the volume. And I'm sorry, but with my poor artistic skills, of course, those reactors are not the exact same length. But let's say for each one of these, the volumetric flow rate is 1/3 V0. Okay. And the volume was 1/3 V1. Okay. So in this case, right, we would have said that the conversion was equal to some value, right? We're just going to call it X star. And in all of our previous examples here, where we were kinetically controlled, the conversion coming out of each one of these was also the same value, right? Because we could always scale down. But that begs the question here. We just did a whole bunch of stuff in class, right? We just spent 35 minutes or so, 30 to 35 minutes, getting things in terms of the velocity and the properties of the particles, and more particularly the velocity. And we talked about velocity in the previous lecture as a very important variable in dictating the thickness of the diffusion layer. And at higher velocities, you had smaller diffusion layer thicknesses, and that meant faster mass transport. So if this is true, right, if the volumetric flow rate is going to be decreased by 1/3, and all we do is have reactors that are the same, have the same area, but we shorten the length of them, is this going to be true for our reactors? So let's look at that a little bit, okay? So a couple of minutes ago, we derived an expression for how the conversion changes with all these different variables, right? We said that the natural log of 1/1 minus the conversion was equal to Kc times AC over the linear velocity times the length, okay? So in this example above, right, in the full reactor, right, or not for this example, but let's say for that part, what we would then say is that the natural log of 1/1 minus X star, right, we'll say that this is in the full reactor, right? And we're going to denote that by a star, that the natural log of 1 over 1 minus x star equals the mass transfer coefficient, right, Kc star, times AC times the reactor length divided by the velocity, right, of that particular case. But let's look at the case when we split the reactor, right, into different sections. And I'm going to denote those with dashes over the numbers instead of stars. And we're going to say that that's the natural log of 1 over 1 minus x with the line over it equals Kc with a line over it times AC times the length over our velocity, okay? Where we've split the reactor into, I mean, the example I did above was 3, but we'll generically do it for n, and then we'll show specific examples. So let's just divide these two, right? I want to try to relate these. So let's simply divide what's going on in split reactor divided by what's going on inside of our original reactor. And if we do that, right, the left-hand side would be the natural log of 1 over 1 minus x bar over the natural log of 1 over 1 minus x star is equal to Kc bar times AC times L bar over U bar divided by Kc star times AC times L star over U star. Okay? Now, looking at this, right, you might think, oh, all the terms are going to cancel, right? But remember, we just said this in the last lecture. We know that that's not true, or at least we would think that the Kc's might cancel. But that can't be true because Kc is equal to, remember, 0.6 times dAB to the 2/3 over the kinematic viscosity to the 1/6 times U, the velocity to the 1/2 over the diameter of the particles to the 1/2. And so if we look at that, well, what this means is that if you had the same particles, let's not mess with the particle diameter at all. So if we're just going to change the velocity, but we have the exact same catalyst in both reactors, well, then Kc bar over Kc star would just equal to all these things would be constant in that case, right? Where you didn't change the particles and all the temperatures and everything were the same. So that would just be equal to the square root of the velocity U bar over the square root of U star. So that transforms our relationship here just a little bit. So now the thing on the left-hand side here, the natural log of 1 over 1 minus x bar over the natural log of 1 over 1 minus x star, now that's going to equal this ratio of Kc bar over Kc star, right? So this is U bar to the 1/2 over U star to the 1/2 times, now the ACs are the same, right? Because we're going to have the same reactor. So those are going to cancel. And now we have different reactor lengths. So this is still L bar over L star. And then we also, from this division, have U star over U bar. Okay. And so this thing at the end of the day just equals U star to the 1/2 over U bar to the 1/2 times, and I apologize, I'm getting a little close here, so I'm just going to move this over, times the reactor length, L bar, over L star. Okay. So what does that mean? Well, if we broke things up into three or into multiple or n parallel tubes, right? So what this really is equal to U star over U bar to the 1/2, right? Times the length over L star. And if we wanted to split this up into a certain number of tubes, well, it's related, or these are then related by the number of tubes. So for example, U bar is just equal to N times U star, right? Essentially, we're saying that, is 1 over N times U star, right? We're breaking it up into N stages. And the same thing with the length, right? This length is equal to 1 over N times the thing that we called L star. So if we want to make this substitution, then the natural log of 1 over 1 minus X bar over the natural log of 1 over 1 minus X star is just equal to, substituting these things, the square root of N divided by N, where N is the number of tubes that we've broken this up into. So above, right, I gave a generic example where there were 3 of them, right? And in a kinetically controlled process where we don't have KC, right, these didn't change, right? The conversion was always the same. And we solved a couple of problems where we broke things up into different stages. As a matter of fact, I remember a PFR lecture saying that it never makes any sense to break up a PFR, right, for the purposes of conversion. Now, there are other things you could do that for, or other reasons you might want to try. So when N is equal to 3, right, in that example that I gave above, right, we could actually look at this. Well, let's say if, I'll pick a value for X star. Let's say that equals 0.9. Well, then when N is equal to 3, X bar is equal to 0.73. If N is 4, X is 0.68. If N is 10, X is 0.52. And the reason that this is happening is because as you split the reactor into different sections, the volumetric flow rate is going down. And so when that happens, the velocity goes down. So the diffusion layer goes up, or the diffusion layer thickness increases. And that leads to slower mass transfer coefficients. And that leads to lower conversion. And so we have to think, from an engineering perspective, you don't always want to have one huge reactor for redundancy, right? What if it failed? Then you'd be making nothing. What you'd really like to be able to do is to break things up to have redundancy. If one thing fails, maybe you just make less of what it is you're trying to make. You take one tube offline and you continue to run the rest of the process. So how would we get around this, right? How then, if we had a mass transport limited reaction, would we do this? Well, some of it is, we know that we have to increase the velocity. Now, there's 2 sides to that, because you also decrease the residence time when you do that. So mostly what you would have to do here is to design your system with the ability to tune the velocity, and also perhaps even to make the reactor length a little bit longer than you would from a design perspective. And this helps to build redundancy into the process. Of course, it adds cost, but nothing's more expensive than having a facility that is doing nothing. And so a little bit of initial capital cost and operations cost over time is going to offset your possibility for a catastrophic failure, or that your one reactor would die. And you can think of that cost as an insurance policy that's going to help you to smoothly run that facility. And it's not uncommon at all to have reactors that are either just exist in parallel and you just switch between them, or that you will have multiple tubes that will then undergo maintenance in a rotating schedule. So it gives you the opportunity to always be doing the maintenance that you need to do to keep the reactors operating it also gives you capacity in case one reactor fails, that you can dynamically respond to that, and that you don't sacrifice the quality of your product. All right, as promised during the main lecture here, I want to talk a little bit more about this variable AC, right? And we said that AC is equal to the catalyst area divided by the reactor volume. Okay, now how could we be a little bit more quantitative here? And how do we get to a functional form like the one that we had in the main lecture? Well, we can do that by saying that, look, this catalyst area over reactor volume is really related to properties of the catalyst itself, and also how the catalyst is incorporated into the packed bed. And so the latter, I'm going to say, is basically just a catalyst volume divided by a reactor volume. Right? That's just the portion of our reactor that is occupied by the catalyst. Okay. Now, if we think about that, well, the first thing is that it tells us there's multiple ways that you can pack a catalyst together. But the other side to that is that we need properties of the catalyst itself. And to do that, and to get to catalyst area over reactor volume, I need some quantity that is the catalyst area divided by the catalyst volume. And if you look at this, the first term here is related to how we put the catalyst in the reactor. The second term here is somehow related to the catalyst itself. And so if we start to think about these term by term, so this here is really just the fraction of the volume that is occupied by solid particles. And we often think about that as related to porosity, or it's actually 1 minus the porosity. So if you had no particles, right, it would all be open space. And if theta is related to the catalyst itself and how much space is actually there, well, the catalyst volume over the reactor volume is really just 1 minus the porosity, right? So there's 1 minus theta. Now, what about this second term here, the catalyst area divided by the catalyst volume? Well, this is just a shape factor of the catalyst itself. And you could think about this. We could have spheres, we could have cylinders, we could have unusual shaped pellets, right? So this is just simply related to the catalyst. Now for spheres, right, which is the thing that we've been thinking here, well, this term for a sphere is just the area of the sphere over the volume. So that's just pi times the diameter over 2 squared, or we've actually called this d sub p, divided by the volume, which is of course just 4/3 times pi times the diameter over 2 cubed. And if we look at this, right, this is just 1/4 pi times the diameter of the particle squared divided by, then this becomes 4/6 times pi times the diameter of the particle cubed. And of course, those 4's cancel, and that just becomes 6 divided by the diameter of the particle. And so therefore, for spherical catalyst particles, we know then that AC is just equal to 6 times 1 minus the porosity over the diameter of the particle, which is what I showed in the main part of the lecture. But the thing that I want to really point out here is that we could have any shape of catalyst that we want, and we can still use this term AC to describe our system, and we'll get some practice doing that later this semester.